Okay, so I have 4 examples for you of the polar coordinate problems. Okay, so we're going to go through each one. All right, so this first one, we need to find the area. It's a very simple area problem. It's not a simple problem, but it is a simple area problem. So we're not doing anything more difficult than finding the area. Bounded by the curves, r is equal to cosine theta and r is equal to sine theta. So r is equal to cosine theta and r is equal to sine theta, we've graphed before. So those are 2 circles that look like this. They both have radius 1. So one looks like this. Okay. And the other one looks like that. All right. So the region bounded by those 2 is this little piece inside here. Okay, so it would be helpful. So as you can see, for us trying to do this problem, we're going to use the fact that we're going to use a radius and an angle. Okay, so when we first start talking about our radius, let me make that black, is going to come up out of here. And it's going to first go to this curve. And then when it gets to this point right here, it now is sweeping out the area of the other curve. Okay, so it first does the area of the top curve going around to here, and then it follows the area of the side curve. Okay, so that's what we have to do. So if this is our radius, it is nice if we kind of knew where these 2 met. Okay, so we'll let r equal the cosine of theta, also have to equal the sine of theta. So that means that the tangent of theta is equal to 1. So that implies that theta is pi over 4. So at theta equals pi over 4, our radius changes. Okay, so from the interval, so when theta is between 0 and pi over 4, then our radius goes between 0 and this curve is the cosine. Nope, it goes between 0 and the other curve, goes between 0 and this curve, and that is the sine of theta.
Wait, I have one more question.
Yes.
How did you get tangent again?
Oh, you divide, so you have cosine of theta equals sine theta, and you divide by cosine.
Okay.
No problem.
Thank you.
You're so welcome. Okay, so you get the dA, which is r dr d theta. And then you have to do the inner, so you can either do twice that area. You can do twice that area because the areas is the same, or you can actually do the second part, which is the integral from 0 to pi over, I'm sorry, from pi over 4 to pi over 2. And r goes from 0 to the cosine of theta, r dr d theta. But I'm going to use the fact that the area on both sides of pi over 4 is the same. So I'm going to make myself nice and happy and just double that first interval. So I'm going to say this. So this is the area. So I'm going to say the area is twice the first one of 0 to pi over 4. And then I'm going to get 1/2 r squared evaluated from 0 to sine of theta d theta. So the halves and the 2 are going to cancel. So I'm going to get the integral from 0 to pi over 4. And then I'm going to put in sine of theta, sine squared theta, d theta. So then this becomes 1/2 the integral from 0 to pi over 4 of 1 minus the cosine of 2 theta d theta. So we use the double angle formula. So I get 1/2 theta minus 1/2 the sine of 2 theta evaluated between 0 and pi over 2. So that gives me 1/2. For theta, I'm going to get pi over 2 minus 1/2. And the sine of pi is 0. This ain't the right answer. Why ain't this answer the right answer? Why is this answer not the right answer? I know why. Because I put in pi over 2 and it should be pi over 4. I just made up my own problem. That should be pi over 4. So this should be pi over 4. So this should be pi over 4. And now I end up with the sine of pi over 2. So now I get 1/2 pi over 4 minus 1/2. And that is correct. Okay. All right. Question on that one?
No, I will have to rewatch it. All my questions probably be coming to you Monday. Like a lot.
Okay. Please catch up, sweetie.
Okay, thank you.
You're doing okay. You can be doing better. I know you're working and stuff, but just try to catch up. It's a lot. Okay. So compute the integral of this function, x squared plus 2y squared, on the domain where all the x, y are real numbers, y is greater than 0, x is greater than 0, and I'm on an annulus. Okay. So for this one, you can see that x squared plus y squared is between 1 and 2. So if I graph the first one, the first one is x squared plus y squared is equal to 1. Okay. And the second one is x squared plus y squared is equal to 2. Okay, so the region is all the stuff in here. So it's between the two circles. X squared plus y squared is between the two circles. So that's my region. I don't mind being not filling it, but I don't want to go outside the region. So that's why I redid it. Okay. So the reason why I would want to use polar coordinates is because anytime I have a circular region, I want to use the fact that x squared plus y squared is r squared. So here I'm basically saying r squared is less than or equal to 1 to 2. So therefore r goes between 1 and the square root of 2. So my radius goes like this. Undo it. Undo, undo. Oh no. What did I do? What did I do? What did I do? Okay. So my radius only goes from here to there. And it sweeps around, goes all the way around. So theta goes between 0 and 2 pi. And then I'm integrating that function. So I need to figure out what that is. So f of xy is x squared plus 2y squared. There are many ways to simplify this. One good way is to just take x squared, pull off 1y squared, and then add on another y squared. So x squared plus y squared is r squared. And then this is r squared sine squared theta. So this becomes r squared times 1 plus the sine squared of theta. So that's the function. So therefore, we want to compute the integral. Theta goes from 0 to 2 pi. The integral r goes from 0 to the square root of 2. The function inside is r squared times 1 plus the sine squared of theta, and r dr d theta. Okay. So I'm integrating the integral from 0 to 2 pi, the integral from 0 to the square root of 2, and this is r cubed 1 plus the sine squared of theta. I can actually move that out. D theta, and the integral from 0 to the square root of 2 of r cubed dr. Okay, so that's not a hard integral. The first piece is the integral from 0 to 2 pi. I have 1 plus 1/2 minus 1/2 the cosine of 2 theta, d theta, and then this becomes r to the 4th over 4, evaluate between 0 and the square root of 2. So this piece right here is 1. Yeah, that's just 1. I think. Yeah. Square root 2, square root 2 is 2, square root 2, square root 2, 2 times 2 is 4, divided by 4, 1. So this piece is just 1. So then this is the integral from 0 to 2 pi of 3/2 minus 1/2 the cosine of 2 theta d theta. Okay, so this integrates to 3/2 theta minus 1/4 the sine of 2 theta evaluated between 0 and 2 pi. And the only thing that's going to come out of there is 3/2 times 2 pi, which is going to be 3 pi. Okay, question?
No.
Okay. All right, so now this one, this is x, still don't have no space. This is x, still don't have no space. Right big. X squared plus y squared. Okay, so that's e to the negative x squared plus y squared. And the domain is theta goes between 0 and pi, and r goes between 0 and 2. Can you draw that? Anaya, you gonna draw that?
Can you draw? I'm not good at drawing. I don't like drawing things to see it.
How are you gonna do this test, boo-boo?
I have to draw on the test.
Well, you need to know some of these domains, yeah.
Oh my gosh.
Yeah. So, okay, so it's a circle because we're talking about r being between 0 and 2. So we know we got a circle. Okay, but r goes between 0 and 2. But theta goes between 0 and pi. So we only want the top half. So I can erase off the whole bottom half because there's nothing there. And so this is the domain. That's my region R. So this is an easy problem. So I'm doing the integral, theta goes from 0 to pi. R goes from 0 to 2. The function is e to the minus x squared plus y squared is r squared. And then I need r dr d theta. That's it. That's all that is. That's a nice, easy problem. Okay.
Mm-hmm.
This is the integral from 0 to pi d theta. And then the other piece is 1/2 e to the minus r squared, evaluated between 0 and 2. So you get pi.
Where did you get 1/2 from?
So if I let u equal to e to, nope, u is equal to minus r squared, du is equal to minus 2r dr. And then, and I'm missing a negative. And then rdr becomes negative 1/2 du. So when you substitute everything back in, negative 1/2 pops out.
Okay, I see what you did. Thank you.
Okay. Okay. Very good. So I'm going to pull the 1/2 out, the negative 1/2 out. So when I put in a 2, I get e to the negative 4 minus 1. So I get 1 minus e to the negative 4 times pi over 2. All right. And then the last problem . Okay. So find the volume between the sphere, x squared plus y squared plus z squared is 1, and the cone. So this is an ice cream cone. Oh, why did I say ice cream cone? I just thought maybe I should drive down to Baskin Robbins. Oh, geez. Life is hard.
You love drawing the cones and stuff.
I know one thing. I now want to go to Baskin Robbins. And I don't need to. Okay, there you go. That's all that's needed. Okay, So I can see that as I'm doing this, Z is going to start at the cone and go up to the sphere. Okay, so Z is going to start down at the cone and go all the way up to the sphere. So Z top is the square root of, so obviously because everything has x squared plus y squared in it, I'm going to switch over to polar. So now I have r squared plus z squared is 1, and z is equal to r. Okay, so this now becomes z is equal to the square root of 1 minus r squared. So now r, which is the cone, is less than z, is less than the square root of 1 minus r squared. Okay, so now we have a bound on z. Now what we need to find is what is the region in the xy plane. So what's the region on the ground? So we got to find r. So how do you find r to project down? What do I do? Anaya, where you go?
I'm still here.
Okay, how do you find the region that you're integrating over?
I thought you just found it. Or
No,
that's just
we have to find r, the region in the xy plane. We got to find r, the region in the xy plane. Okay, we
you
found.
set them, huh?
Yeah, that's right. Go ahead.
Set them equal to each other.
Okay, that's good. All right, so therefore we get z equal to r equal to the square root of 1 minus r squared. So set them equal to each other. So we get the square root of 1 minus r squared is equal to r. So 1 minus r squared is equal to r squared. So 1 minus 2r squared is equal to 0. So therefore, r squared is equal to 1/2. So r is equal to 1 over the square root of 2. So they intersect in that circle. So the circle they intersect in is easy. Here's the circle they intersect in.
Is this similar to like 5.4?
This is 5.4.
Oh, because I feel like this looks like 5.4.
Oh, I didn't teach you this.
Oh.
I'm sorry.
I thought you did a problem like this yesterday.
If I did, I might have. Okay. This is triple integration. Yes. Yes. It all just runs together. And I just kind of wasn't thinking.
No.
This circle is r is equal to 1 over the square root of 2. So now you know that r goes between 0 1 over the square root of 2. And in order to cover the whole circle, theta has to go between 0 and 2 pi. So you are right. This is triple integrals and polar coordinates, which is section 5.5. But guess what? It was good practice. It was still good practice, even though it's not on the test. It was good practice. So the volume.
Wait, so what section are on the test? 5.3, 5.4, and
5.4, not triple integrals and polar coordinates.
so it's just 5.3 and 5.4?
No, your test is 5.1 through 5.4.
Okay.
Yes, 5.1 through 5.4.
Okay. Yeah. Thank you.
So the volume is the double and triple integral over the thing dv, but unfortunately I just cheated and didn't realize I wasn't supposed to do this, which is r d dz dr d theta. I'm sorry. Okay, but it's not hard. Theta goes between 0 and 2 pi. R goes between 0 and 1 over the square root of 2. Z goes between R and the square root of 1 minus R squared. And then you end up with R dz dr d theta. Yeah. Sorry. I didn't realize that when I was picking the problems that we weren't doing triple integration in polar coordinates, but it did help with you understanding polar coordinates a little bit more. So what I should have done is I should have done the problem in Cartesian coordinates. So let's go back and do it in Cartesian coordinates. So if we were to do it in Cartesian coordinates, so let's do it in Cartesian coordinates. Cartesian should always be spelled with a C as far as I know, capital C. Okay, so let's go back and do the same problem in Cartesian coordinates. All right, so I'm going to double click my square. I'm glad you said something. Okay, so in Cartesian coordinates, we still have to find where they intersect. Is that the same problem? No, that's the wrong problem. That's the wrong problem. I grabbed the wrong problem. Here's the problem. Okay. Okay, so in Cartesian coordinates, it's even easier to set up the integral because Z is going to go from, Z still going to start at the cone to the sphere. So therefore you're going to get Z is going to go, this is going to be 1 minus x squared minus y squared. And then this is going to be the square root of x squared plus y squared. Okay, so that's where Z goes from. Okay, then we found out that we're going to set them equal. So when you set it equal, you have x squared plus y squared plus z squared, but z squared is x squared plus y squared again. Is equal to 1. So you get 2x squared, 2 times x squared plus y squared is equal to a half. So you get y is equal to the square root of 1/2 minus x squared. Okay. And then x has to start here at minus 1 over the square root of 2 and end here at positive 1 over the square root of 2. So therefore your volume, x is going to go from negative 1 over the square root of 2 to the positive 1 over the square root of 2. Y is going to go from the bottom half of the circle, which is negative square root of 1 minus x squared, to the positive square root of 1 minus x squared. And z is going to go from the square root of x squared plus y squared to the square root of 1 minus x squared plus y squared dz dy dx. And if that was the integral, I would tell you on the test, because I have worked the problem out beforehand, that you don't have to compute that integral. I would do setup, but do not solve. Because I don't want you to try to solve that. That's pretty ugly. That's pretty hard. Up. I see a mistake. That should be a minus y squared. Yeah. Okay. You have any questions?
Yes. How did you get the 1 minus x squared? I see how you got everything else, like the
That
1
should
half.
be a half.
Oh, okay.
A half. That's what happens when students pay attention. They figure out your mistakes, and that's what you're supposed to do. Catch them all, because you go home and be like, I don't know where that came from. Yep, that should be there.
So the negative, so the 1 over the square root of 2, that's how you got that one from inside of the radical. The
Okay,
first part.
so the circle, remember, in the Cartesian, in the XY plane, right?
Mm-hmm.
We had this circle. So in the Cartesian plane, we have x squared plus y squared is equal to a half.
Okay.
All right.
Mm-hmm.
So when you solve for y, you get y is equal to the positive or negative square root of a half minus x squared. So the top, member, a function, this would fail the vertical line test. So this top half of the curve is the positive square root of 1/2 minus x squared.
Oh, I wasn't talking about that part. I see how you got that. I'm talking about how did you get, it says from the first steps. So that's the second one. How did you get the first one? 1 over the square root of 2.
Okay, so if y is 0, that's this point and this point, right?
Mm-hmm.
So when y is 0, on the circle, you get x squared
Mhm.
is equal to a half.
Oh, okay. Thank you.
This
That
point.
makes more sense.
Yep. Yep. Good question. Good question. Good question. You got it going on. Okay. Any other questions?
Now, what are your plans for next week? Like in regards to lessons?
Okay, hold on. I'm gonna stop this.